So for my next application of integrals, I want to take a look at work. No, I don't mean the work I've been making you do every single day. I mean in the strict physics sense. So why is it that integrals show up so much in the natural sciences, in classical 17th century, 18th century, 19th century, and so on? It's because integrals allow us to compute so many of the things that scientists want to talk about and engineers want to talk about. Now, I do need to give a crash course here on what is actually meant by the term work, and do forgive me if I get some of the pronunciation wrong. I am not a physicist. So, there's a difference between sort of the colloquial term work, of course, like when you're doing homework, when you are doing work for a job. In physics, it's a more technical definition involving force. So forces push or pull on objects. There's the force of gravity, which keeps us tethered with the crust beneath our feet. These are all examples of forces. The force of wind on a blustery day, and so on. So, if you have a path where you are pushing or pulling some object, we want to know the force that's being used. And so Newton gives us, various laws of motion. So the force on the object is defined in the second law of Newtonian physics. Force is equal to mass times acceleration. Wait a minute, I've been harping on acceleration for weeks now. Acceleration is a kind of derivative. It's the second derivative. So force is equal to mass times, let's say, d squared s on dt squared. All right. Well, what can we do with that? So we do want to be careful about what units we're using. If we're in the metric system, then we're working in newtons appropriately enough. A newton is equal to 1 kilogram meter per second squared. In the US system, the fundamental unit of force is the pound. Alrighty. So work is pretty easy to calculate when you have a constant acceleration, right? Work is just equal to force times distance. Well, that's not too hard at all. I didn't even need calculus to find the amount of work it takes to do things. But in practice, when we are working in physics problems, if you go on to be a physicist, it is not very often that we get to work with constant forces. So just a bit of unit analysis here. If F is measured in newtons and D in meters, then the work is going to be measured in Newton meters, which is called a joule, or in the US system, a foot-pound. And we can calculate work, say the work amount of the work required to move things off of the floor. So if I wanted to take a book which weighs 1.2 kilograms and lift it from rest and raise it up 0.7 meters, how can I calculate the amount of work? Well, again, I just multiply. Super duper simple. And these are the very beginnings of calculating amount of work for various actions taken. But again, we will see it gets much more complicated.